rocks of the Earth's crust are different things to different people. They are a source of academic study, aesthetic pleasure, physical recreation. But above all, and to all of us, they are resources. Human life as we know it would be impossible without rocks and what we extract from them. Our world depends on rock. Our earliest ancestors made their homes in rock and left their mark on them. Rocks have built our homes ever since, and our great public buildings. Often sedimentary rock, especially limestone, has been used. But igneous or metamorphic rock can also be building materials. For centuries, marble has been the most desirable of the decorative rocks, beloved by architects and sculptors alike, not only for its appearance, but for the ways it can be carved and shaped. More humbly, slate has provided the roofs for millions of simpler houses. Today, we see more glass, brick, and concrete than stone. But concrete is, after all, essentially a mixture of stones and cement is 2/3 limestone. Brick is clay, another rock, baked hard to make it durable. Glass has sand and powdered limestone as two of its main constituents, while stone aggregate is an essential raw material for road making. But all these uses are concerned with the physical character of rock and not with its composition. It's only for the outer parts of the Earth's crust that we can work out a likely chemical makeup. Some 47% of the crust is oxygen and 27% silicon. 8% is aluminium and 5% iron. Calcium is 4%, sodium and potassium 3% each, and magnesium 2%. But copper is only 1 part to 10,000, and lead is only 1 part to every 50,000. And these elements seldom exist as such. They exist as minerals. Most of them occur as silicates. In coarse granite, they can be seen quite clearly. Both quartz and feldspar are silicates. Both are very common rock-making minerals. Quartz is silicon dioxide, and one of a number of minerals which form crystals. In its pure form, it's colorless. In recent years, quartz and silicon have found many uses in electronics and telecommunications. The silicon chip has made possible the production of miniaturized circuits, for example, and thereby the development of computers. One of the main uses of feldspar is quite different. In certain conditions, the feldspar in granite is liable to chemical decomposition. Very simply, it rots. It becomes kaolin, a fine clay known also as china clay. Kaolin is widely used in the manufacture of paper and in the pottery industry. It is washed out of the quarries with powerful jets of water. Quartz sand is washed out too, but that will be separated out before the kaolin is refined. So how are mineral deposits formed? First we look at sedimentary rocks and fuels. One of the oldest fuels and the basis of the Industrial Revolution is coal. This is anthracite, a particularly valuable coal because of its high carbon content. Like all coal, it needs little or no processing before use, only separation from the other rock around it. Coal has its origin in the dense vegetation of the tropical swamps some 300 million years ago. As this vegetation decayed, the swamps became burial grounds for a rotting forest. The debris was organic matter, rich in carbon. Peat is a kind of halfway stage in the creation of coal from this organic debris. Peat is already a fuel, though not a very efficient one. Here it is being cut and stacked in the traditional way. Peat is about 55% carbon. Anthracite, 95%. It is the pressure of later sediments laid on top of the peat that converts it to coal. On the whole, the greater the pressure, the purer the coal. Coal can be extracted either open cast, as here, or mined underground if the seams are particularly deep. Modern mining is highly automated. The surface structures of modern mines can blend very discreetly into the landscape. As with coal, we need oil and gas as fuels. And as with coal, they too have their origin in decaying organic matter. Not this time a rotting forest, instead a carpet of remains of tiny sea creatures and organisms. As this carpet thickened, bacteria promoted the processes of decay and change. A seabed sludge formed, rich in carbon and hydrogen. The creation of oil had begun. Millions of years later, under pressure from sediments above, this oil can migrate. If the rock above the source rock is porous, oil can push upwards into it. The oil will continue its progress until it meets a layer, or cap, of impermeable rock. It can go no further. The oil gathers in the porous rock beneath the cap. A reservoir has been formed. It is such reservoirs that the petroleum engineers hope to find and develop. Unlike coal, oil, as it comes out of the ground, is useless. Before it can be marketed, it has to be refined. The oil industry is comparatively recent, only a little over 100 years old. In comparison, the coal industry is much older, though the uses of coal have changed. The main use of coal today is in the generation of electricity. Another valuable group of minerals provides us with metals. As old as the mining of coal is the making of iron. This is how it was done a couple of centuries ago. It was a mere 3,500 years ago that human beings started to make iron tools and implements. We find iron as an ore. An ore is an accumulation of minerals valuable enough to be worth working. This is limonite, a low-grade ore found in sedimentary rocks, with only a quarter of its content actually iron. This is hematite. It occurs in older igneous and metamorphic rocks. It has 2 to 3 times the iron content of limonite. Hematite often occurs in this kidney-shaped form. Iron is one of the most common materials of the Earth's crust. The richer ores are the ones most in demand, usually mined open cast. The ore is often taken long distances to the areas where it'll be refined. In the world today, more iron ore is shipped than any other dry bulk commodity. Low-quality ores are usually mined only when they are found near to their market. A third variety of iron ore is magnetite. Like hematite, this is often a high-grade ore, but unlike limonite and hematite, it's magnetic, hence its name. The high-grade ores used nowadays are often shipped in pellet form for ease of processing. The iron will be separated out in a blast furnace. The ore, essentially an iron oxide, will be placed in the furnace with carbon in the form of coke. Limestone too will be added. It will merge with impurities in the ore to make a slag. The ore, coke and limestone are heated with extra oxygen. The carbon combines with the oxygen to form oxides of carbon, leaving the iron as pig iron. The pig iron will go on for further processing in the iron and steel industries. Today's world has been built with iron and steel. Yet the world's first great iron structure is not much more than 200 years old, and its epoch-making steel structures not much more than 100. The world's aluminium industry is also only just over 100 years old. Aluminium is one of the most common elements in the Earth's crust. Its main ore is called bauxite. Here, the bauxite is being carried on covered conveyors from mine to refinery. Bauxite is found mostly in tropical or subtropical lands, where over millions of years, the aluminium in the ore has been concentrated by the weathering of other elements. Bauxite is aluminium oxide and water. Frequent impurities are silica, as sand, and iron oxide, which gives bauxite its reddish color. The conversion of bauxite into the metal aluminium is a two-stage process. The first stage is to purify the ore. This is done by treating it with heated caustic soda. A virtually pure aluminium oxide is separated out. It is called alumina, a fine white powder. The metal aluminium can only be obtained following a lengthy process of electrolysis. Electrolytic smelting involves passing a powerful electric current through the alumina in reduction furnaces. In these furnaces, the oxygen in the aluminium oxide is combined with carbon. The pure aluminium is siphoned off as a molten metal. The oxides of carbon have been removed as furnace gases. The aluminium is usually cast as ingots before going on for further processing. Aluminium is a light metal, which after alloying is easy to work. It can be cast, cut, rolled, shaped, even extruded. Aluminium has found many uses. Many minerals occur as veins or lodes. Such veins were originally fissures above an igneous intrusion. Hot watery solutions circulated through these fissures, minerals crystallizing from these solutions as they cooled. We call these hydrothermal deposits. Among ores created in this way are sulfides of copper, zinc, and lead. Copper ore often contains less than 1% copper, so an enormous amount of unwanted rock must be moved to obtain the copper. At the Bingham mine in Utah, 100,000 tons a day. Copper is one of the oldest metals worked by mankind. As an alloy with tin, copper was the basis of the Bronze Age, some 5,000 years ago. A form of pyrite is the source ore of copper. This is the most common form, iron pyrites, sometimes known as fool's gold. The ore for copper is a variant, chalcopyrite, a sulfide of iron and copper. To obtain the copper, the ore is first ground to a fine powder. Then the different sulfides in the ore are separated out in flotation tanks. Other minerals, like zinc and lead, are often found with copper. In a smelter, these sulfide concentrates are roasted and converted to oxides. Here, the molten copper is being poured out to make anodes, for final purification nowadays is usually achieved by electrolysis. This process involves immersing the anodes in sulfuric acid, through which an electric current is passed. This causes a chemical recomposition, depositing pure copper on the cathodes. We use 9 million tons of copper a year. It's an excellent conductor of heat and of electricity. About half the copper we use is for the carrying of electric current. Sphalerite, zinc sulfide, is the source ore for zinc. Sphalerite is sometimes known as blende. Zinc is separated out in much the same way as copper. Alloyed with copper, zinc becomes brass. The major use of zinc is in coating steel to prevent rust, and the major process employed is hot-dip galvanizing. We use about 7 million tons of zinc a year. The source ore for lead is galena. Although lead and zinc ores are often found with copper, they also occur frequently on their own. For centuries, lead has been used on buildings. The world now uses some 5 million tons of lead a year. The major use for lead nowadays is in the manufacture of car batteries. This is cassiterite, or tin oxide, the principal ore of tin. It's normally found on the margins of certain granite areas. It's often recovered from river deposits, washed out from the original veins. We use over 10 million tons of tin a year. Because of its density, the tin can be sorted from the gravel fairly readily. Tin is non-toxic and resists corrosion. So one of its major uses is in the coating or plating of steel when making cans for the food industry. The so-called tin can is less than 1% tin. Tin is also one of the main metals used in soldering, as an alloy with lead, for example. Gold is another metal often recovered from river deposits. the metal has been washed out from veins and lodes related to igneous intrusions. The gold rush prospectors used pans, flumes and sluices to find and recover the precious metal. Modern commercial extraction is very different. Gold can often be mined open cast. At the other extreme, the deepest mines in the world are gold mines, up to 3,500 meters deep. The value of gold makes it worthwhile. An ore with 1 part gold in 100,000 is considered a rich ore. Human ingenuity will always find a way to extract a valuable mineral. But at a cost. This was one of the world's first great copper mines 200 years ago. 100 years ago, this was one of the centers of the world's tin industry. Copper and tin, lead and zinc. These are some of the minerals that are becoming scarcer. Their higher grade deposits are gradually being depleted. No mine lasts forever. Sometime in the next century, we'll need new or different sources. One solution is to use lower grade deposits of these scarcer minerals. This means research is needed to develop the technology of processing low grade ores. We need to find more economic ways of obtaining the minerals from such ores if we are to continue to mine them. Other minerals we have in abundance. The world has enough iron and enough aluminium to meet its needs for as long as we can foresee. The world's resources of coal should last for centuries yet. And while supplies of liquid petroleum will diminish, there are still large deposits of oil shells and tar sands which can yield oil at a cost. Oil and gas have already been found beneath our seas. Other minerals surely exist. Human ingenuity can surely recover them. And we can recover and reclaim the old mining areas. A few decades ago, there was a working coalfield here. Now the land is reclaimed for agriculture. Other sites have been reclaimed for amenity use, providing pleasure for thousands. The scarcer minerals can be reclaimed and recycled. We cannot afford to throw away the irreplaceable, and we must only use the scarcer minerals for what they can do best or do uniquely. Copper from old piping, lead from old batteries, even aluminium from cans. All can be reclaimed and recycled. We can't recycle fuels, but we can develop devices which use renewable sources of energy, the wind, the sun. And we can use all our fuels with more care and responsibility. We can use even the Earth itself. The inner geothermal heat, which forged our rocks and minerals, can also be harnessed to create our electricity. It would be fitting if the heat that created our habitat could also provide the energy to keep it habitable.